Hi, I'm Kristine Haley. I work in the Island Nanoscale Lab in the Department of Physics and Astronomy. And today I will be discussing electronic states of the 1T type tantalum disulfide polymorph. So to begin, what is tantalum disulfide? I'll refer to it as Tas2 to keep it short, but tantalum is a transition metal, which means that it's a great conductor of heat and electricity. And when you work with nanomaterials, you quickly learn that this piece of Tas2 that sits on a fine-tipped tweezers is massive. The fact that we can see it with the naked eye means that it's too big. So I care more about its crystal structure. So if we zoom in, we can see the side profile of the crystal lattice. There is a layer of tantalum atoms that are sandwiched between sulfur atoms. And if you look at the top down of that plane and focus on the tantalum atoms, you can see that they have a hexagonal structure. Now, Tas2 has quite a few polymorphs. A polymorph are substances that have the same chemical composition, but they differ in their atomic arrangements. And different polymorphs have different stabilities, which depend on their bond to neighboring molecules. Today we will be discussing the 1T type, but just as a comparison, there is a 2H type, and you can see that they do have different atomic arrangements. So when I say electronic properties, I'm really just curious about what the electrons are doing. What state are they in? How are they behaving? Because these electron effects give rise to really interesting and cool phenomena. One of these being superconductivity, which is kind of crazy because it's a quantum phenomenon that you can see macroscopically, where resistance at some temperature drops to zero and magnetic fields are completely expelled from the material. There is also a hidden quantum state. This transition is unique because you can excite your material with a short laser pulse, and by doing so, the resistance drops by about 3 orders of magnitude. It basically undergoes an insulator to metal transition, and this state is extremely stable and a reversible process. So the main topic of today are on charge density waves. And in order to discuss charge density waves, we need to know what a Fermi surface is. So bear with me, but a Fermi surface is a surface in momentum space which separates occupied from unoccupied electron states at zero temperature. So in a metal, the electron density is highly uniform and atoms will remain in their equilibrium positions. But as you change temperature, the Fermi surface becomes unstable, and this instability leads to a redistribution of the charge density. So here we see a gap in the band structure when previously it was continuous. Now, my research is focused on the commensurate charge density wave, which occurs at low temperatures, and the nearly commensurate charge density waves, which occur around room temperature. And so in the commensurate phase, we see a Star of David pattern. So there's 12 tantalum atoms with one central tantalum atom. And the entire crystal lattice consists of these structures. And at room temperature, these structures kind of form into hexagonal domains. So the question here that we're asking is there a magnetic field dependence at this phase transition? And does the thickness of Tas2 play a role? In order to make these measurements, I first have to create devices. And the problem with Tas2 is that it degrades in air. So I create devices inside of a glove box, which pumps out oxygen and water and allows me to work in an inert atmosphere. It is extremely important to work in a clean environment because any degradation or defects along the way can alter and hinder electronic properties. So to make nano devices, I exfoliate two materials, one being Tas2 and another being boron nitride. Now, boron nitride is served to sort of just encapsulate the Tas2, so when I take it out of the glove box for wire bonding and experimental measurements, it won't be subjected to air. So to begin, I take the bulk form and I exfoliate it. For us, exfoliation is done with tape. It's called the Scotch tape method, where you take a layer off of the bulk parent and you just continuously fold the tape, and by doing so, you reduce its dimensionality. Afterwards, I'm able to screen for flakes using an optical microscope. So here is an image of TAS2. The area of interest is this really transparent region, which is about 5 layers thick. We also have a flake of boron nitride, which again just serves to encapsulate the TAS2. We usually look for flakes that don't have cracks or defects or are around a lot of adhesive like this green stuff because it makes them more difficult to pick up. So how do I pick up flakes? Well, I use a glass slide and I create a bubble on one end. So I use a little piece of rubber and then I put a piece of tape over that rubber, which creates the bubble, and that gives a little bit of height dimension. And then on the very center, I put a drop of clear nail polish, and that allows us to actually pick up flakes. So for an example, I have my TAS2 that's sitting on top of a substrate, which are both sitting on top of a stage of a microscope. This glass slide is attached to a piece of equipment called a micromanipulator, which just allows for very fine precision in X, Y, and Z. And so I use that micromanipulator and I go down and I use a lot of heat application, and then eventually I can pick up the flake. After I pick up the flake, it sits on the glass slide, and then I just transfer it using the same method onto electrodes. And so here is what that looks like. So after completing a device, this is what it looks like. So outlined in red is my TAS2, and outlined in purple is my boron nitride, which again is just encapsulating the TAS2. Now, if you zoom out just a little bit, you can see that the device is sitting around gold lines. And if you zoom out a little bit more, you can see that these gold lines are attached to larger gold pads. And if you zoom out quite a bit more, you can see the entire circuit board. And so we place this device into a cryostat that can be lowered to really cold temperatures at 2 Kelvin, which is the same temperature as outer space, and also allows me to use magnetic fields. So we first measured the bulk TAS2 device. You can see the device layout right here, but if you look at the resistance and temperature plot, you can see that there's a phase transition occurring from about 140 Kelvin to about 225 Kelvin. But what's really interesting is if you zoom in to around the 220 Kelvin area in this little inset, you can see that there's a shift in temperature that depends on whether or not the field is positive or negative. So the green indicates 0 Tesla, the red indicates a -2 Tesla, which occurs at a higher temperature, and the blue line indicates 2 Tesla, which is shifted to a lower temperature. So we performed the same measurements with the thin TAS2. So right here you can see what the device looks like. But on this one we did sweeps of 1 Tesla to -1 Tesla. But you see the same shifting in temperature that's depending upon the field orientation, whether or not the field is positive or negative. So again, at a positive field, we see a shifting in the temperature to lower temperatures, and at negative fields, the temperature shifts higher. So to conclude, we see that by applying an external magnetic field brings forth a magnetoresistance effect, which is just saying that the resistance of the material is sensitive to the orientation of the magnetic field. Now, we don't fully understand why there's this polarity dependence. It could be something to do with the domain walls from the nearly commensurate phase transition, or it could also be something due to the band structure, but more research needs to be done to have a concrete explanation. Thank you.